We have talked about the different laws of thermodynamics, namely the first law, second law and the third law. Just to remind you that the first law talks about conservation of energy, while the second law talks about how the internal energy or the change in internal energy is connected. A part of it is spent as work done and the heat that is given to the system. And we have also looked at third law, which sets a lower limit of entropy at T equal to 0 when all the thermal motions cease. Now, we have also seen that the mathematical form of this the first and the second law combined is written as du equal to Tds minus Pdv. U is the internal energy, T S are the temperature and the entropy, P is the pressure and V is the volume. Here S and V are independent variables and that is why they are varied, whereas T and P are dependent variables. Okay. So, these variables actually come in pairs such as PV and TS, and as I said that one of them is independent and so it is varied, the other is dependent. So, here S and V are changed independently and that is why they are called as independent variables, and P and T are dependent variables, just for the sake of repeating. So, now consider that the internal energy is a function of the independent variables, okay. And thereby what we will do is we will derive the thermodynamic definition of temperature and pressure in terms of the internal energy. So, if U is a function of S and V, I take a differential of that. So, when I take a differential, I will have to take a du and this du is equal to say for example, del u del s. So, you change s at constant v and this is ds and plus a del u del v at constant s dv, which is what is written here. So, du equal to del u del s ds plus del u del v dv, and if you compare it with the combined form of first and second laws, then we can immediately identify that the temperature is given in terms of the internal energy and the entropy as del u del s at constant v, and the pressure is actually a minus del u del v at constant s. Okay. In addition, we have looked at the response functions. What is meant by response function is that how does the system respond to a certain external stimulus, and this could be temperature or this could be heat. So, if you want to define specific heat, it is basically dq dt, and from second law dq is nothing but Tds. So, this is T del S del T. Cv is defined at a constant volume and Cp is defined at a constant pressure, and in addition to the specific heat, there are two more response functions that we would be using or we may need. One is called as a thermal expansion coefficient beta, which is equal to 1 over V del V del T P, and the isothermal compressibility, which is denoted by kappa, which is equal to minus 1 over V del V del P at constant temperature. Okay. So, these are T and P are the dependent variables which are expressed in terms of the internal energy and the independent variables, and as well we have discussed this response functions, that is how the system responds to it. So, Cv and Cp have been discussed earlier. This is the expansion coefficient, that is how the volume of the system responds to the temperature change, that is called as a expansion coefficient or thermal expansion coefficient. And compressibility, it means that how much the system is compressible. We will see these concepts more as we go along. Let us now start discussing a classical ideal gas, which is a prototype system of thermodynamics. In fact, it is the simplest system of thermodynamics which we most of the time we talk about. Consider a classical ideal gas, and the word classical means that it is encoded in this energy expression, where Pi is a continuous variable, okay, and that is why it is a classical variable, that is why it is called a classical gas, and it is ideal again because of the same energy that is written here, that is there is no intermolecular interaction, that is all the molecular interactions are neglected in defining the classical ideal gas. And we have seen this earlier, that the equation of state which means that there are these thermodynamic parameters P, V and T, not all of them are independent. In fact, they have a relationship between them which we call as PV equal to NKT or PV equal to RT, where R is nothing but NK and this R is called as the universal gas constant and K is called as a Boltzmann constant. Now, the same equation, that is for a real gas, the equation of state for a real gas is slightly different. It is P plus A by V square into V minus B equal to RT, and all these A and B are some parameters which talks about that these finite size of the molecules and so on and so forth. Okay. So, mostly we will talk about this PV equal to NKT unless we talk about a real gas, not an ideal gas, then we will talk about this equation of state that is written here. So, what are the properties of this classical ideal gas? What can we learn from them as a thermodynamic system? What are the different thermodynamic parameters that one can derive out of this? And in order to do that, we have to define what is called as a Maxwell's velocity distribution. And if you look at the last slide here, so this is nothing but a sum over I half m I v I square. Okay. So, that is all the energy that it has, that is the kinetic energy. Now, this v I, that is velocity of this individual particles. Now, it is very easy to understand that all particles cannot have the same velocity. Just like in a statistical sense, all people do not have the same nature, or all students do not do the same performance. And in a similar sense, that this V I actually refers to, or rather there is a distribution of velocities for these particles. So, some of them are faster moving than others, and this is encoded in this Maxwell's velocity distribution, who proposed that it is equal to 1 by V. This V is nothing but volume, that is a normalization factor. And then there are m by 2 pi k T whole to the power 3 by 2, and then there is a Gaussian term which is written as minus m v square by 2 k T. So, this form is easy to derive, but we are not deriving this here, but we will just tell you that the rationale behind this proposal is that all these v square. So, f of v square, that is equal to v x square plus v y square plus v z square, and all these velocities in different orthogonal directions, they have to be independent of each other, which means f v x square would not depend upon f of v y square and f of v z square, where f denotes a function, and this function is written here, which this comes from this normalization. And why it is normalized? Because it is a probability. So, the probability that you have the particle velocities are distributed between v and v plus dv is given by f v dv. Okay. Since it is a probability, the total probability for V to be between minus infinity to plus infinity, and minus infinity means that it moves in the say leftward direction, and say plus infinity moves that it moves in the rightward direction, or plus velocities mean they are moving rightward, and negative velocities mean that they move leftward, and they can have any velocities ranging from minus infinity to plus infinity. Okay. So, once again just coming back to this point that we said, this f of v x square, f of v y square, and f of v z square are independent of each other, and the only function that would satisfy such a product relation that is independent is that there is an exponential either plus or minus. Now, this plus sign does not make sense, because the plus sign will not allow this probability to be conserved, or probability to be equal to 1, the total probability, rather it will blow up. So, the only plausible sign is minus sign, as I said that this 1 over v m by 2 pi k t whole to the power 3 by 2, it comes from the normalization. So, if you really want to write it for one direction, I will write it as 1 over L and m by 2 pi k t whole to the power half, because I am just taking one direction, and this will be minus m v x square by 2 k t. Okay. And in 3 dimension this can be trivially generalized with a factor of 3 by 2 and L changing over to v. So, this is how the f of v, or the probability. So, this is really f of v that looks like as a function of v in meters per second. You see it is a bell shaped or a Gaussian distribution, and this Gaussian distribution has an average which is given by this red color and written within angular brackets. So, this is the average velocity, and this V p, or sometimes it is called as V m p, is the most probable speed. Okay. And V r m s is a root mean square speed, and it is actually easy to sort of derive expressions for that. Let me show you that in just a while. So, let me show it here. This is again a plot which shows this probability to be for 3 different temperatures. So, as you see that with increasing temperatures, so the blue one is for 100 Kelvin, the next the green one T2 is for 300 Kelvin, and this 300 Kelvin you will come across a number of times. It is typically taken as a room temperatures, which is like 27 degrees centigrade. Okay. In summer of course, it could be larger than this, but that is like a prototype temperature that is taken. And the way we can calculate V p is that we have this distribution, and we can take this of this distribution and put that equal to 0 at V equal to V p. Okay. So, V equal to V p. So, this will give you the most probable speed. Okay. Similarly, you can calculate V average by taking this V and this f of V dV from minus infinity to plus infinity, and this is an odd function and this is an even function. So, the this integral would vanish if you do it between minus infinity to plus infinity. So, we can set the 0 of this to be at. So, this is at this is taken as 0 unless there is a skewness of the distributions. For the this distribution, for this Gaussian distribution, this V can be shown to be 0. And here So, this what 0 means is that it is the middle of the distribution. Okay. It is a value that is shows the peak of the distribution, or that which is given by this integral of this f v dv. Coming to the RMS, RMS is defined as the root mean square. So, what you do is that you have to calculate this quantity, and this quantity is can be obtained by first taking a v square and f of v dv and from minus infinity to plus infinity. So, I take the average of v square. Now, v square average is not equal to 0, multiplied by the distribution, integrate over all velocities from minus infinity to plus infinity, and then you take a square root of that. So, it is a root mean square velocity, and this is an important quantity as well in this distribution. Any distribution will have, there are certain things such as the mean value of the distribution, then the root mean square or the full width at half maximum, and so on and so forth. Okay, so, if you use all of them, then this comes out as, so V p comes out as root over of 2 kT over m. V average would come out as, at a given temperature, it is root over 8 kT by pi m, and V square is or rather the root mean square, let us call it as a VRMS, as we have defined VRMS. So, VRMS is equal to root over 3 kT by m. So, if you take this ratio of all of that, Vp is to average velocity is to Vrms, this comes out with a root over 2 is to root over 8 over pi. You see kT over m in under square root is always common, and this is square root of 3. So, you know that the Vrms is larger because 8 over pi is something between 2 and 3, because pi is like 3.14. So, if you divide it by that, so it is 2 point something, there is a 2 here and there is a 3 here. So, and once again we show that here as the temperature increases, the height of the distribution goes down. So, as it goes down from T1 to T2 and to T3 farther, and at 500 Kelvin it becomes very broad with the mean value shifted towards larger and larger velocities. Let us now look at what is called as the equipartition theorem. The statement is very important. The statement says that the energy per harmonic degree of freedom per particle for a system at an equilibrium temperature T in one dimension is given by E equal to half kT. Okay. So, this is an important statement. It says per harmonic degree of freedom. This is an important thing, because there could be a different number of harmonic degrees of freedom. We will see that in just a while, and we are just defining it per particle, but if you want to define it for the system, then you multiply it by n, and this is one dimension, that is why there is a half factor coming, and just like in the next line we have written that in 3 dimension it is 3 by 2 kT. So, this energy is equal to 3 by 2 kT in 3 dimension per harmonic degree of freedom. So, if you have more than one harmonic degree of freedom, you will have a 3 by 2 kT plus a 3 by 2 kT and so on. Now, classical ideal gas in 3D has just this as p square over 2m. Okay. There is a pi square and sum over I am just writing the just for one particle. So, it is a p square over 2m, Now, there is just one harmonic degree of freedom P, and because of that it is in 3D, it is a 3 by 2 kT, just what we have said at a temperature T. Now, for an harmonic oscillator we have a P square over 2 m plus a half m omega square r square, okay. And that will tell you that there are two harmonic degrees of freedom, which one corresponding to the P variable P, that is momentum, and the other corresponding to the space variable, which is r, say for example. So, this is let me write it without this vector for the moment, and they mean the same thing basically. So, it is a P square by 2 m plus half m omega square r square. So, we have a 3 by 2 kT and a 3 by 2 kT. So, this will give us 3 kT. So, this is what equipartition says, and this last one we will see that when we get deep into statistical mechanics, this has a very interesting consequence, that the specific heat of solids at large temperature goes as 3 R, which is called as a Dulong-Petit law, and specific heat would be just the temperature derivative of this energy. Okay. So, that will give us a 3 R when you multiply it by N. So, N k is equal to R. Alright. So, let us try to calculate the pressure exerted by an ideal gas, and this is will give us the equation of state that we are quite familiar with. And how do we calculate the pressure? All these molecules, gas molecules that you see in the container are moving randomly in all directions. So, take a particular direction and say that a molecule impinges on the say the right side or right edge of the box, and it returns back, okay. And this has to be considered as an elastic collision, and there will be no change in momentum. So, that it is elastically it returns back. So, the incoming momentum is mvx, considering this as the x direction. So, it is mvx, and the change in momentum would be minus of minus mvx, which is nothing but equal to twice of mvx. Okay. So, it is twice of mvx. Now, in order to calculate the force, we take this twice of mvx multiplied by the Maxwell's velocity distribution, or the probability of these particle to have a velocity between Vx plus dVx is we multiply it by that and divide it by 1 over L, and we know that the pressure is obtained from the force by dividing it by this area. So, I divide it by L square and I get 1 by L cube, and then you integrate this. You can do it in 3 dimension as well, will give you the same result, and one gets a nkt over V, where L cube is equal to V, and this is the equation of state. So, this very simply one can calculate the pressure exerted by a classical ideal gas, and which is nothing but gives you the equation of state, which is P V equal to nkt, as it should. So, let us do entropy of an ideal gas. Let me just do a few steps along with you, and this entropy we know by now it is a measure of disorder. It is and a system left to itself according to second law would always proceed towards increasing entropy. So, how do we calculate entropy of such a gas? Okay, so, let me write down the same equation that we have written earlier, which is a combination of the first and second law. Okay. So, du equal to TdS minus PdV, and our u is equal to Cv into T. Okay. So, this is the definition of specific heat, which is Cv equal to u by T or u equal to Cvt, and we use the equation of state, which is Pv equal to nkt. I will be using this Boltzmann constant rather than the gas constant in most of these cases, but if you are more familiar, and some of the books actually prefer using the universal gas constant, where n k is nothing but equal to r. Okay. So, now we can arrange this equation 1, and using these we can write down the change in entropy, which is equal to a C v dt over T. So, this du by T, and du is nothing but C v dt, C v is of course a constant, plus n k dv over v. Okay. So, this is the equation number 2, and this we have to integrate in order to get this ds. And so, if you integrate for integrating, we will integrate it from some S 0 V 0 and T 0 to S V and T, and doing that would get us S equal to S 0 or S minus S 0 equal to it is a C V log of T by T 0, as you can see that this dt over T. So, it will give you a log, and when we do it from initial temperature, integrate it from initial temperature T 0 to a T, it will give you log T by T 0, and so this is n k log of V by V 0. And we are allowed to club these two logarithms because you know that log of A, say for example plus log of B, this is equal to log of A B, and we can do that, and we can write down this equation as S is equal to, so I write it combining the logarithm. So, S equal to S 0 plus n k and log of T to the power 3 by 2 into V T 0 to the power 3 by 2 into V 0, and that is the entropy of a classical ideal gas. So, all right. So, now let us discuss this mixing of two gases. So, what I mean by that is that suppose you have a container like this which has a partition, you have a gas here which let us call it as A, and you have gas here as well, let us call it as B, and at some point you open that. So, this can be thought of as you open this and allow the gases to mix. Okay, so, the gases would mix eventually, and A and B will get mixed. So, what will happen is that now you have the total volume available. So, this had say for example, V 1 and this had V 2, and there are these number of particles being N 1 and N 2, and now the composite system will have a volume which is V 1 plus V 2 and the number of particles being N 1 plus N 2. So, if you do that, then the entropy would become equal to, so S equal to S 0 for the mixed gas for this combined system, it is equal to plus N 1 plus N 2. This N is being replaced by this N that you see here is replaced by N 1 plus N 2, and we have other terms which are written as a k and then a log of t to the power 3 by 2 V 1 plus V 2 and there will be a term which is T 0 3 by 2 and a V 0. Okay. So, this from a combined volume it goes to a term which is V 1 plus V 2, and as you see that S is an extensive quantity, however, temperature is an intensive quantity and hence it does not change. So, the change in entropy is given by delta S, which is S minus S 0 is simply equal to if we open all of them, it is N 1 plus N 2 and K log of V 1 plus V 2 and a minus of N 1 K log of V 1 and minus N 2 of K into K log of V 2. So, this is for the combined gas, and these are for the individual gases. Okay. So, this is the change in entropy, and this looks fine, excepting that we will see that in just a while. Let us just put that both the gases to have equal volume. So, V 1 equal to V 2 equal to V over 2 and N 1 is equal to N 2 equal to N over 2. This just to create simplification in the calculation, or rather this expression that you have just seen. So, delta S comes out to be a very simple expression which is K log 2. So, that is the change in entropy when you allow mixing of two gases, each having a volume V 1 and number of particles N 1 and a volume V 2 and number of particles N 2. So, it is goes from N 1 V 1 and N 2 V 2 to N 1 plus N 2 and V 1 plus V 2 with a common temperature T. The change in entropy of the gas is given as K log 2. So, that is a positive number, and like log 2 is like 0.693 and you multiply it by the Boltzmann constant will give you some number. But now that makes you ask a question, what happens when both the gases are identical? Let me box it, because if both gases are identical, then there should be no change in entropy. Okay. So, the answer is that there should be no change in entropy. And which means delta S is equal to 0, but we are getting delta S to be a number by just calculating what we just saw, and this gives rise to a paradox, and this paradox is called as Gibbs paradox. As such, this classical physics will not offer any explanation how to get around that paradox or how to resolve this seemingly contradictory notions. But when we go to quantum statistical mechanics, that is we accept the indistinguishability of particles, that is the particles are no longer classical, but they are quantum mechanical, then this automatically this Gibbs paradox is resolved. So, Gibbs paradox will be resolved using indistinguishability of particles. And this is certainly not a domain of classical physics, and we shall see that later. Coming to what is called as a chemical potential, there is another important concept that will be there throughout the statistical mechanics, and it is defined with a symbol mu. And in non-isolated system, that is system in contact with the surroundings, that there can be exchange of particles in addition to exchange of energy. And chemical potential is work needed or work required to add one particle to the system. It is like an extra student comes in the class, and you would think that if there is a bench available, suppose there is a bench or a seat available, this extra person will sit in that, the extra bench which was previously unoccupied. But that does not happen for a gas, because this added particle will not be at rest. So, the entire assembly of particles, all the other particles will have to move and rearrange in order to come to an equilibrium temperature, or rather come to an equilibrium at a temperature T. So, there is some amount of work required in order for this equilibrium to be established, and chemical potential really gives you that work done or that energy needed in order for the equilibrium to be re-established. We will see that for a fermionic system, which are in the sense that they obey Pauli exclusion principle. So, they are hardcore, one does not in a single energy state or a single quantum state, it does not allow two fermions to occupy with the same quantum numbers, and that is why there is a distribution that appears, which is called as a Fermi distribution, and the chemical potential, which means that there are no other energy states that are available. So, a new particle added would have to sit, or rather would have to be occupied in an energy level at the Fermi level, or at the Fermi energy. We will see that. It is important to note that a photon gas has no chemical potential, or rather its chemical potential is equal to 0, and the reason is that you keep photons inside a container, and photons are going to be exchanged continuously with the surrounding. So, there is no way that you can keep the number of photons to be constant inside a container, and that is the reason that the free energy of the gas, photon gas, is independent of the number of particles, because so if free energy becomes independent of the number of particles, you will have the chemical potential to vanish. Okay. So, let us deal with an open system where the number of particles are they remain non-conserved, and there are now a more number of variables that are going to be required. So, we need more number of variables for these exchange of particles. So, our P, V and T, and along with S and U etc. Are not going to be sufficient. And in that case, this same old combining the first and second law can be written as du equal to TdS minus PdV minus mu dN. Okay. And this mu dN is the new term, and this is the chemical potential multiplied by the change in the number of particles. We had earlier seen that u is a function of these independent variables, which are S and V, and now we change this to u, which are s, v and n, where n denotes the number of particles. So, du becomes equal to del u del s with v and n constant plus del u del v, sorry, with a ds, del u del v with s and n constant with a dv plus a del u del n with s and v to be constant with a dn, and then term by term. Now, I just call this as equation 1 and this as equation 2. So, if you compare between equation 1 and equation 2, you can simply see that S is defined as I mean S is nothing but, so T is nothing but del u del S, which we have already seen. However, what one does here is that one introduces a new energy functional, which we have discussed earlier, is the Helmholtz energy, which is u minus T s. So, F is the Helmholtz free energy. So, this is u minus T s. So, using that one can define S to be equal to, in terms of these new energy functional, which is del F del T V n, P is equal to minus del F del V. We will see these expressions several times when we do statistical mechanics, and mu is equal to del F del n with T and V. Just a while back I was talking about photon gas, and I said that the free energy or the Helmholtz free energy is independent of the number of particle, and that is why mu is equal to 0. So, del F del n equal to 0, and that is why mu equal to 0. So, these are the now the definitions of these entropy, pressure and chemical potential which we shall use. Now, let us calculate the chemical potential of an ideal gas, which is nothing but F del F del n at a constant T and V. So, let us take this equation for the entropy that we are familiar with, which we have derived just a while back. So, S is equal to S 0 plus N k log of T to the power 3 by 2 V and T 0 to the power 3 by 2 V 0 and so on. Okay. So, I mean your T is same. So, we can write it as T to the power 3 by 2. So, F is equal to u minus T s, which we have said, and u is nothing but C V into T. We have seen that as well. So, this is minus T s, and this is equal to T into C V minus S. So, that is the expression for F. We are slowly trying to get at F to be a function of n, so that we can take the derivative and can get this chemical potential. And C V is equal to 3 by 2 N k. This is the specific heat of a monatomic gas. Which is easy to see, because we have from the equipartition theorem we got the energy per particle as 3 by 2 kT, and C V is simply del u del T, or C V into T is u. So, we can get the C V to be 3 by 2 N k, and there is just one degree of freedom, which means monatomic gas that we are talking about. So, the free energy then can be written as, so this is equal to 3 by 2 N k T minus T s, and this is equal to N k T log of T to the power 3 by 2 and V there is a minus. So, this and t to the power 3 by 2 and V naught and so on. Okay. So, that brings us that your mu, which is equal to del f del n according to the definition with T by V equal to 3 by 2 k T and minus k T log T 3 by 2 V divided by T 3 by 2 V naught, and that is the definition of chemical potential in terms of all the parameters of the system. It is more customary to replace V by P using equation of state. And once we do that, we get a equation which is k log P plus 3 by 2 k T minus k T log of n k T to the power 5 by 2 and T to the power 3 by 2 V naught and so on. So, this is the expression for chemical potential of a classical ideal gas. So, in terms of all these parameters that are P, T, etcetera, and so on. So, this is the amount of energy needed to add a particle to the gas, okay, to introduce a new particle to the classical ideal gas. Okay. So, let us do one example problem, and this example problem is about in the PV diagram a process, a thermodynamic process is shown, or rather a reversible thermodynamic process is shown. Mn is an isothermal and Nk is adiabatic, and Kl is nothing but, so this is isothermal, this is adiabatic, and Kl is the pressure is constant. So, it is a isobaric, and this is a volume being constant, it is isochoric. And then it says that fill in the table for different thermodynamic quantities which are the enthalpy, delta W which is work done, delta U the change in internal energy and change in temperature. So, if you look at Kl, which is an isobaric expansion, which means P is constant. So, the gas does work on the surrounding, which means delta W is equal to 0. Now, since the volume expands, the density decreases. So, the delta T has to be greater than 0. So, that is why it is written by plus and plus here, and for an ideal gas this is important that U is only a function of temperature for an ideal gas. So, this delta U increases because delta T increases as well. So, that is why this is also positive, and your delta H which is enthalpy which is delta U plus delta W. So, both increase, and so delta H increases as well. For the other isochoric cooling, we have delta V equal to 0. So, work done goes to 0 because work done is PdV, and again delta T is 0 because the gas it happens at a constant volume. So, the delta t is less than 0 and delta u is less than 0 as well, and all these. So, that is what is shown by negative, and this is 0, work done is 0. So, delta h is negative as well, because both delta u and delta w are negative. Similarly, for the isothermal compression, delta T is 0. So, we first get delta T equal to 0. Delta V is shown to be lowered, that is delta V is less than 0. So, the work done is less than 0 here, and again delta U equal to 0 and delta H, which is the sum of delta U and delta W, because your delta W is negative, this is again negative, and so on. Then the adiabatic compression is corresponding to delta H equal to 0, and delta V is less than 0, delta W is less than 0, because it is a compression, volume goes down. So, delta W is less than 0, and so on, and then your delta U would be greater than 0 and delta T is greater than 0 as well. Okay. So, go through it slowly in order to sort of convince yourself that all these what is increasing and what is decreasing along various paths in the PV diagram, they are all correct. We shall stop here and continue with a new topic in the next meeting.